Go ahead, Yaroslav.
Okay, thank you for coming, everyone. So, I will present some parts, some results of the paper, which is called Mathematical Perspective on Transformers by Geshkovski, Letrouit, Polyanskiy, and Rigollet. And you see the link. And actually, how can I? Yeah. And let me first remind you what is transformer model is. So this is about, so this is about neural network architecture, which consists of several parts. I will define it in several minutes, but was first introduced around 8 years ago, and now it is widely used in the task of natural language processing, computer vision, and reinforcement learning. And this basically works with any sequentially organized data by what? So let me define the model here. Actually, what I actually need is to define encoder and decoder blocks. So they basically consist of multi-head attention layer, add norm layer, feed forward layer, and then just producing any linear layer with then putting it in softmax function. And so this basically consists of what? So we just put in an input x to linear transformations, three linear transformations, namely queries, keys, and values, which are denoted by q, k, and v. And then we put them, I mean q and k, into softmax function, which is defined, as you can see, in the left bottom corner. And
Right bottom corner, right?
Yeah, right bottom corner. Sorry. And then yeah. So this is and then you just take this as a matrix. Here is P by P, and apply it to vector V. And then, so this is a multi-head attention. Then add a norm layer is what? This is basically we add the input and the output of multi-head attention layer, and then put it into the layer norm layer, which actually just puts projects the every p every p coordinates into the sphere. Spheres are like different for any of the p coordinates here, and then you just put it into the feed forward layer, which might be actually very different with very different activation functions, like the original paper they used Rigollet activation function, but for example, for BET model, which I will introduce in the next slide, authors use like GU activation function and many other options possible. Okay, so then after you put this as, so this was basically an encoder layer, and the decoder layer is what is just putting output of encoder layer of encoder block, sorry, applied n times into the each layer of decoder block by Q and V. And K is basically formed from key value, basically formed from decoder block, which looks mostly the same. Okay, so this was a quick reminder. So actually, there are different versions of transformer architecture. Like, for example, you can just omit any decoder part or any encoder part. So with just encoder part, you will just have a BERT model, and with just decoder part, you will have just GPT model. Okay. So what about this? So let's continue to the results of the authors, and this is basically the setting is about what? So we just put so we just investigate the transformer activation dynamics. So we just do what? We apply this softmax matrix here, which you can see is this part with 1 over z and sum of exponents, and multiply it by a vector of v here. And then just project the velocities on the tangent tangent subspaces of d minus one dimensional spheres, where d is, I remind you, is the dimension of your model, dimension of your data. Okay.
So you have here summation over j, but not over I. Yes, that's the idea.
Yes, because you have I here, right?
Of course, yeah.
Mm-hmm. So this is for n different i's. Mm-hmm. Okay, so z is basically the denominator, which you might consider as partition function. Okay, and actually, what I discovered during the reading of the paper is that I actually need to read two additional papers, and I will somehow introduce the results from both three of them. And so in this paper, authors consider the dynamics for transformer model with Q, K, and V matrices equals to being equal to identity matrices. And they consider two different dynamics, which numerically looks very similar to each other. So here we have division by this partition function z, and here we see just division by the number of by the length of your data.
So
Okay.
this is basically taking beta to 0, right? Then your partition function becomes n. Yes.
No. Well. If beta equals 0, then yes, they are they.
No, I am just saying 1 over n is the limit of beta going to, yeah.
Yes. And well, Yes, so if you're not interested in this USA model, you might just consider this SA model if you for the last part of my talk here. So just probably ignore this USA model, which this is actually somewhat well. This is actually the some approximation of this dynamics. Okay. So this dynamics was like well, this is based on the paper on sync-formless architecture, and yeah, actually, later I will discuss the cases when Q, K, and V matrices are not equal to identity matrix, and but for now, let's continue with the
But one
result.
question about the P orthogonal. It's in the orthogonal, so you project that resulting vector in the space orthogonal to xi. Is that the idea?
Yes, yes. This is a tangent subspace of tangent space of your sphere.
Right. So basically, you're
S
just allowing
minus one.
rotations of x.
What?
You're just allowing rotations of x, right? You want x to remain normalized.
Yes, actually, we'll normalize it in layer.
Yes.
So
Yeah.
yes. So this is so basically we just put this x's to this x to this manifold of n times of d minus one dimensional sphere. Yes. Okay. So this dynamics actually acts on probability measures of your on your sphere, on your I don't know how to do how to name this. Let's call this manifold as multisphere, and so this basically acts as a
It's a product of
on,
spheres, right?
yes, products of spheres. I don't know for short. Let's just call it multisphere.
Sure.
Okay, and so just we just consider these equations as the gradient flow of this in the form of in this form. And no, this sorry, this is not a gradient flow for now, but as some flow on your on our manifold, and where measure mu is being equals to okay. I just didn't copy paste it correctly, but okay, so just like statistical interpolation of your of any of your measure, and like for example, well, for your data, yeah, for your data element, and then for general acting is for any measure mu, you might consider this functional, and then with z equals to this integral. Okay, so you just so you just act on your measures in this way, and actually what the authors are interested in this one. So they just try to state that well, to prove the conjecture that actually in lots of cases this dynamics converges to just single delta measure with for lots of cases. So which was like previously stated conjectured from experiments, and this actually happens for like For when? So for small betas with a probability of almost 1, with small betas and sorry, I don't remember. Yes, for small betas, this is just converges every time. Yeah, for small enough betas. Yeah.
So, Yaroslav, can I ask you about the setup
Yes.
about mu? Now, so if you can go back.
Mm-hmm.
So,
Yes.
so, so, uh, so this is the activation dynamics. So you're assuming that you like execute this first equation many times on some
Mm-hmm.
state vector x.
Mm-hmm.
That's the idea.
Yes.
But then you have also mu inside there, and mu will be presumably changing together with x, right? Because x.
Mm-hmm. Yeah. Here it is.
Uh, no, well, no. The first one is just continuity equation, or unless I don't understand what it is. This is just okay. It's
Yes,
just a
but
continuity.
you have a dynamical part here.
Okay. Okay. So it's
Derivative over t. Yes.
okay. So mu is a distribution on the state space of x, and you're saying it will just okay. Then it's just rewriting the first equation in terms of
Yes.
distributions, right? Okay.
Yes.
So
Mm-hmm.
there's like no learning dynamics here at all. This is just that was my question. So there's no learning
No, these papers are not at all about any learning
learning.
dynamics.
Okay, I see.
Just
So they
just
just take an
about activation
architecture and
dynamics.
see, okay, what's happening inside of. Okay, understand it.
Mhm.
Perfect. Thank you.
Yes, so yes, thank you for the question. Actually, since we fixed uh, Q, K, and V matrices, which are actually learnable parameters
Mhm.
in transformer models, so we just consider the activation dynamics here.
Sure.
Yeah.
Mhm.
Mhm. So this tends to just singular measure with like pointwise measure with for small temperature beta, and for big enough temperature beta this also holds, and for big dimension of d, I mean at least 3, this holds always for all betas.
Mhm.
Okay.
So basically, it's saying like after multiple applications of activation map, it gets to a fixed point. That's what.
Yes.
Yes, got it.
Mm-hmm. Yes, but there are some nuances, and I will tell
Sure.
somewhat later about them. Okay. So actually, what I found in this paper is that actually previously authors made another paper with actually lots of experiments, and I didn't fully read it, this paper, so I just present the results here. Okay, for this previous paper, and this paper considers the cases when you do not need query key and value matrices being equal to identity matrix. So this was just like a simple degenerate case, but for like general cases, you might see the results of what will be the limiting geometry of your measure mu. So you just so they just tend to like actually probably for now I realize that I don't understand how to formulate the results. So which is what is the limit geometry? Do they mean actually? Yeah, sorry about this, but okay. So this is not a single point here. Like, so this is like a single cluster, pointwise cluster, and it's near the infinity of time t, it will be like single cluster for q, k, and v equals to identity matrices, and for several cases too, for several other cases too. So and actually, I'm not sure how to formulate these results on limit geometry for now, but yes, this is just for the reference here. That other cases being investigated too. Okay. And actually, well, I consider that I won't have enough time for making any proofs of these theorems, but okay, so for the original papers that I'm talking about, this is like the proofs are based on the negations of properties of this functional and some concentration inequalities techniques from probability theory. Yeah, and actually they're very too long for this talk. And okay, so there was a continuation of this work like this year.
So why do they call that
Previous
energy? I mean,
years.
maybe I have a still question about it. Why do they call this as energy? I mean, what's the? I mean, I understand that this is scalar.
Actually, probably this is from like
Is it-
how to say this? Actually, I didn't study this field thoroughly, but this seems to me for like energy functional in the sense of differential geometry. So actually,
I still
probably
don't.
I need to study deeper, but this like a standard term in differential geometry. Yeah.
Yeah, I
And
wouldn't call this standard, but okay. So let's
well,
take
well, no, yes, okay.
the limit of beta equals to 0, which is what they're investigating, right? That's their
Mhm,
limit.
mhm.
Is
Okay.
it limit?
Very limit.
The theorems that they proved that they only work for small beta, right? That was the idea, or no?
Well, for low dimensional cases, they only work for small beta.
For small beta. Okay, so
And for large dimensional cases, like at least three-dimensional, they work for all betas.
okay.
Mhm.
Okay, fine. We can discuss why this is called energy later. Yeah.
Okay. So actually, there was a continuation of this work. Like there was like the about activation dynamics of this transformer model and of this SA and USA models. Yes, let me remind you these ones right here. And they actually uh, found out in the in this paper that actually the learning dynamic, sorry, activation dynamics is um, very slow, like in the start or in the middle of your activation dynamics. Like this is like for exponentially big time, it is very, very slow. So it converges very, very slow, and then it converges rather big, rather rapidly. Okay. So actually, they just produced the peaks for this, and yeah. So the last part of my talk is about giving you some visual information about these dynamics. So so they consider this gradient flow dynamics on manifold for some function E.
So that manifold is your multisphere, whatever you call it.
Yes,
Okay,
multisphere.
and you did say that it was not a gradient flow. Now you are simplifying and assume that it is.
Yes. Actually,
It isn't, right?
yes, I didn't put it out, but for SA dynamics and no, for USA dynamics it is basically a gradient flow for
No, it
some
isn't. No, it
logarithm
isn't.
of z. What?
No, it isn't. There's, x. It's not a
Uh,
gradient flow. You have. So what is
uh,
the V then? What is the potential for which it's a gradient flow? Maybe it is. Maybe I just don't see it. So what is the V for which it is a gradient?
Actually,
Doesn't look
okay.
like a gradient to me, but
Okay, actually, I don't remember it now. Yes, I just forgot to put it out, but
I'm sure in
uh,
some limit it can be considered as a gradient flow,
mhm, mhm.
but doesn't look like one.
Uh, yes, actually, I don't remember it now for exact formulation.
Mhm.
Maybe I can look into the paper, but
Sure. No,
whatever.
but as an approximation, okay, fine. Let it be a gradient flow.
Well, okay. If you are interested, we can look now into the paper and
Mhm.
found it out. Okay, probably. Which let's see.
Oh no, not now. No, no, no. Let's not do it now.
Not
No,
now.
no, 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 no. Of course not. Sorry.
I don't
Yeah.
remember for now.
No,
Sorry.
no,
Sorry
no,
about
no.
this.
I thought
Uh-huh.
later. Later we can look into it. Yeah.
So they just these so if this E functional satisfies these properties, then there is a theorem that holds, which looks like this, and actually they so if you
So
what
is
are the
this energy
properties?
the same energy that
You
you were
just
showing
project what?
before? Is this E the
What?
same
Sorry.
E that you, is this E the same E that you were showing
Yes,
before the
yes.
energy?
Actually, it is almost the same,
Okay, then we
but
can
you
just
need
take
to
a
divide
derivative
this
with
by
respect to xi and see if it's going to be the gradient. But I don't. Okay, well, I cannot.
uh,
So if we just differentiate it with respect to x,
mhm,
um,
let's
well,
check.
you will get something on front. So it may actually turn out to be the right thing to do. Okay, I need to do the math to confirm. But at
Mhm.
least you will see one of the x's will jump out, and so maybe right.
Mhm,
But then you will
yes,
also, it's not only x that
yes.
will jump out.
One X will jump out, and you just
No, but then you will
have.
also have this matrices jumping out, so it's not clear that this will be the right. Maybe in some limit once again. But again, we have to
Okay.
do the math to check it. Mhm.
Yes. So, okay. So, if this functional satisfies these three inequalities for some constant delta with some with the property of existence of some the so-called slow manifold n. So you just project every u on your multisphere M on this slope submanifold n with this property, and on this slow manifold you just have this inequality. So then you just have this theorem, which is might be considered as classical for now. So you just have that your difference between dynamics of U and V just might be just bounded by above with exponential function. And okay, so it converge. So for converging of your so you just have this very slow convergence of your activation dynamics in the neighborhood of this n, and this will take like lots of time. And yes, so slow manifold they introduced is being defined by these inequalities, well, by single inequality actually, and where they just struggle to derive some this well, any formula for this constant delta beta in their proofs, but actually they just prove it for just dynamics where d equals to 2, and they say that they believe that the same holds for the same proof holds for higher dimensional dynamics. So this is this is literally how they tell this in their article, and yeah. So this is just an illustration of the slow dynamic of the slowity of the dynamics here, and as I
So the slow
understand,
dynamics is a direction, the flat directions where your gradient is small, right?
yes, yes,
Okay, and but anyways, eventually in the infinite time you will get to the minima. That's what
yes,
gradient.
and then it just start to converge very rapidly.
Well, if you get out of this slow gradient
Yes.
mode, but
Mm-hmm.
but the question is that I have, because in that activation dynamics you have a slowdown due to the flat direction, so maybe you can effectively speed it up by increasing the uh, it's not the learning rate, activation rate, right? The steps that you take in those directions, and if it is a gradient flow. So
Mm-hmm.
have they looked at I mean, on the algorithmic, if your job is to get to the fixed state, you can speed it up once you've discovered those flat directions.
Actually, they somehow liberated it, but actually I didn't look
Okay,
into
okay,
it
because
with
that
very
seems to
detail.
be
Yes, but they did it
okay.
for something. Yeah, and yes, actually, this is yeah. So actually, I think that this is the end of my talk for now. Yes, for just actually, I tried to not put put here lots of details, and actually just put some more some sketches of the results. Yes, and yes, that's not all for now. Any questions?
Thank you for your attention
Mm-hmm.
about attention mechanism. Okay,
Yes.
are there
Okay.
questions?
So,
Mhm.
yes, any
There are questions.
questions?
Yeah, so my question, I think I already asked, is to actually confirm that it is a gradient form and see what is the
Okay,
potential
let's
if it
check it,
is. So
probably.
no, but no, we don't have to do it now. No, we'll just do it later. Running out
Mm-hmm.
of
Yeah.
time. So that's the only question I have. And so there is no indication, no reference to the learning dynamics of how to speed up learning.
No.
Nothing like
All the
this.
weights are fixed here.
Okay.
Mm-hmm.
Okay. Now, what if you don't get to a fixed state? I mean, and there is a probability distribute, like, you have really flat directions, like zero directions, and there's actually a probability distribution in the
Mm-hmm.
where you got it. I mean, that doesn't seem to be a problem either, because that just means that your your prediction, your output is just not a fixed state but a distributional state. So that shouldn't be a problem. Or is it? Or do they say that if the transformer doesn't get to a fixed state, it's a bad thing? In other way, is it a
Oh,
bug or a feature? That's what I'm trying to understand.
oh, then your probability for being in this state is low.
Well,
Uh,
you have distribution probabilities. You can be in one, end up in one place or about in the other place. There's instead of like converging to a delta function distribution, you convert uh, to a distribution, probability distribution, which is not
well,
a function.
mhm. I don't know actually if they
Hey, again,
consider
be
it
a
as a
good thing.
bad, but it seems that yes, they consider it in the context of any learned weights of these dynamics, and so they just try to uh, do this
Sure.
for 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 converging to a singular point,
Okay.
to
And maybe
singular beta.
last question I have about beta, because of course in this transformer architecture, the softmax and beta play the key role. Um,
Mm-hmm.
uh, and so the question is, are they investigating how the theorems they prove depend on beta, and what's the right choice of beta, or should the beta be constant for different transformer blocks, or should it change? So have they uh, talked about that at
Actually,
all?
no, they just put it the same QK and V values, so they just have
So it's
the
the same
same
one.
beta for all activation dynamics
Sure.
here, yeah, right? And then they just don't bother about
Sure.
any of changing the beta along the activation dynamics.
Hmm. Right. Perfect. Okay, that's all the questions I had. Let's see if
Mhm.
there's anyone else who wants to. If not, we'll just end the meeting here, and all other questions can be asked in the chat. Thanks everyone for coming, and I'll see you next week.